Imagine a protective shield over the United States. An invisible golden dome in space capable of shooting down enemy missiles before they ever reach American soil. Recently, President Donald Trump floated the idea of such a system. But here's the question. How would it actually work? Could space-based lasers really stop a nuclear attack? And what physics makes it possible, or impossible? That's what we're breaking down today. I'm Ben. This is Physics or Bust. The Golden Dome is going to start with a lot more proven ground-based technology, with the eventual idea of including a satellite-based laser defense system, designed to intercept and destroy enemy ballistic missiles during their boost phase. That is, just after launch, when the missile is still climbing and its engines are firing. We'll dig into the physics in a minute, but first, if you like this video, you'd probably like this book. I've got a link in the description below. I do get a small commission, but it wouldn't cost you any extra. While the phrase Golden Dome is new, the idea isn't. The US has flirted with space-based missile defense since the 1980s Star Wars program under Ronald Reagan. But today, advances in directed energy weapons, DEWs, especially high-power lasers, make the concept far more technologically plausible than ever before. Lasers are attractive for missile defense because they can deliver energy at the speed of light. Unlike interceptors, which require precise timing and a physical collision, lasers just hold a beam on a target long enough to deposit enough energy to weaken or destroy it. Sounds simple enough, right? During the boost phase, when the missile is hot, fragile, and brightly visible against the cold background of space, it's especially vulnerable. But lasers don't magically cut through steel. They work by delivering enough energy per unit area, per unit time, to heat and weaken a target. A high-power laser can heat the missile's surface, melt through structural components, or ignite propellant tanks. But the physics comes down to energy. For a missile traveling through boost phase, the casing might be thin aluminum, or composite material, or steel, but you still need to deposit something like 10 to 100 kilojoules per square centimeter to guarantee burn-through before the missile can maneuver or shut down its engines. That translates into megawatts of optical output delivered for several seconds. And here's the problem. A solid-state laser might have an electrical to optical efficiency of 30 to 40%. That means for every megawatt of laser beam, you need 2 to 3 megawatts of power input. The power has to come from somewhere, and a satellite can't just plug into the power grid, so there's only a few options. Massive solar arrays are one option, but you need football field-sized arrays per satellite. Or maybe later on they can be powered by next-gen compact fusion reactors, if it becomes real. But the most likely option? Advanced nuclear reactors. DARPA and others are exploring space nuclear reactors already. Compact fission reactors designed for multi-megawatt output. Nuclear power could make continuous high-power lasers in orbit feasible. But here's the thing. Even if you have the power, physics tells us that light, including laser beams, spread. Diffraction sets a hard limit on how tightly you can focus a laser. The spot size on the target is limited by this equation. S equals r theta, where theta is 1.22 lambda over d, where lambda is the wavelength of light and d is the aperture diameter of your optics. Suppose you're using a 4 micron wavelength infrared laser, which is common for solid-state lasers. At 1,000 kilometers distance, a 1 meter telescope aperture gives you a beam spread of almost 5 meters wide at the target. To keep that down to a 10 centimeter spot, tight enough to burn, you'd need wavelengths closer to 1 micron and apertures around the 120 meters range. That's nearly 20 times larger than James Webb-class optics, in orbit, multiplied across a whole constellation of satellites. And that assumes perfect optics. In practice, turbulence in the upper atmosphere, satellite jitter, and thermal distortions all make it even harder. Not only that, but a missile in boost phase is a moving, accelerating target. To hold a beam steady, your satellite has to use high-precision adaptive tracking mirrors with pointing accuracy down to the micro-radian scale. That's equivalent to keeping a laser pointer fixed on a 90-mile-per-hour baseball in Beijing with a laser pointer from New York. Sensors have to acquire the target, discriminate between real launches and decoys, and then coordinate multiple satellites to ensure coverage. The physics is unforgiving. Missed by just a tiny fraction, and your beam spreads out, dumping heat harmlessly instead of burning through. And here's the catch most people forget. A 1 megawatt laser in space also creates 1 megawatt of waste heat. In space, there's no air to carry heat away. The only way to reject it is through infrared radiation, which is slow and requires enormous radiator panels. If you don't dump the heat, your own system overheats and fails. That's one reason why sustained firing of space lasers is so challenging. So even if we master the optics and the power, we still have to solve the thermal physics puzzle. Otherwise, the system could be overwhelmed just with the number of launches at one time. At this point, the US and other nations have been working on directed energy weapons for decades. The current focus is on solid-state and fiber lasers. These scale by combining many smaller laser modules into a single coherent beam, a process called spectral beam combining. Instead of one giant laser, you use hundreds or thousands of smaller ones phase-locked to each other. This makes the system more modular, efficient, and reliable. The Navy has already tested 130 to 300 kilowatt solid-state lasers on warships, capable of disabling drones and small boats. The roadmap is clear. Scale up to 500 kilowatts, then 1 megawatt for missile defense. But the holy grail is phased array lasers. Just like phased array radars steer radio waves electronically, phased array optics can steer and focus laser beams without giant moving mirrors. That could allow a large constellation of satellites to act as one giant synthetic aperture telescope, combining beams across multiple platforms. That's cutting-edge physics and engineering, but theoretically achievable. So in theory, physics says yes, a constellation of satellites armed with megawatt-class lasers could engage missiles in their boost phase. Coverage could be global, with satellites positioned in low Earth orbit, approximately 500 to 1,000 kilometers altitude, ensuring at least one platform has line of sight to any launch. But here's the technical reality check. To guarantee coverage, you'll need dozens, possibly hundreds of satellites in orbit. Think Starlink, but armed with lasers instead of internet routers. Analysis suggests that destroying a liquid fuel ICBM would require holding a megawatt-class beam on a target for 10 to 20 seconds. That's a long time to maintain perfect focus, given jitter, clouds, and possible countermeasures. Speaking of countermeasures, hardened casings, rotating missiles, reflective coatings, or simply launching multiple decoys are relatively cheap ways to greatly reduce the effectiveness of this system. Even shortening the boost phase from 300 seconds to 200 seconds makes interception exponentially harder. Launching and maintaining a constellation of nuclear-powered laser platforms could cost trillions. And replacing satellites every 10 to 15 years makes this a forever project, with no cap on the cost. So could it work? Physics says yes, but at enormous financial and engineering cost. It's not a matter of violating the laws of physics. It's a matter of whether the engineering and economics align. Here's the part we can't ignore. If such a laser system can defend against any missile launched at the US, then by definition it could also strike any target anywhere in the world. A Golden Dome isn't just a shield. It's a global sword. It gives whoever controls it the ability to neutralize nuclear deterrence and project power in a way no nation has ever been able to before. And that raises profound questions about international stability, arms races, and whether giving one government that much power makes the world safer or far more dangerous. So is the Golden Dome science fiction or the next revolution in defense technology? The physics is real, the technology is advancing to the point that we could do it, but the politics and economics may prove even more challenging than the engineering. So what are your thoughts on the Golden Dome proposal? Let me know in the comments below. For more space and science updates, make sure to like and subscribe, and remember, keep asking questions. I'll see you on the next video.